The orbits in the Kuiper belt are relatively stable, so few comets come directly from this region. The scattered disk, on the other hand, is much more dynamic and chaotic, and it is believed to be the origin of most short-period comets. Comets coming from the scattered disk initially pass through the region of the outer planets, and are then called centaurs. Over time, these centaurs can migrate further into the inner solar system, becoming the famous short-period comets. To date, we have identified more than 4,800 of them. However, there is an important mystery. Comets lose mass and wear down each time they approach the sun, causing some of them to completely disintegrate and disappear. Despite this, new comets mysteriously continue to appear. But how, after 4.5 billion years since the formation of the solar system, do these icy bodies still continue to appear? After all, where do they come from? What brings them to us? These questions intrigued scientists during the 20th century, especially the Dutch astronomer Jan Oort, who proposed a theory to try to solve this mystery in 1950. Furthermore, Oort also calculated the distance between the solar system and the center of the Milky Way, and was one of the first to suggest the existence of invisible matter in the galaxy. This was based on the movements of stars, one of the initial clues for the modern concept of dark matter. To better understand Oort's theory, we need to go back approximately 4.5 billion years to the time when the solar system was forming from a large, flat disk of materials spinning around the sun. The inner planets, closer to the sun and therefore hotter, became smaller and rocky. In contrast, the outer planets located in much colder regions grew significantly in size. In this icy environment, water existed in the form of ice mixed with dust and other materials. These fragments constantly collided, merging and forming ever larger objects. Even after the formation of the planets, a huge amount of these icy blocks called planetesimals remained, composed of the same material that gave rise to the planets. But the giant planets, thanks to their immense gravity, captured everything that came too close to them. These icy objects were either absorbed or thrown into extremely elongated orbits, with some being hurled toward the sun, while others were ejected into deep space. Trillions of these ice blocks were scattered throughout the solar system, and although each one had little mass individually, their gravitational interactions, when summed up in large numbers, generated significant impacts. Over time, this gravitational dynamic caused Saturn, Uranus, and Neptune to gradually move into more distant orbits from the Sun, while Jupiter migrated slightly to a more inner orbit. During this planetary migration, Neptune had several gravitational encounters with these icy bodies, launching them into chaotic and highly inclined orbits. This rearrangement of the outer planets caused an event in the solar system known as the Late Heavy Bombardment. Today, these objects are distributed in three main regions. The first is known as the Kuiper belt, named in honor of the astronomer Gerard Kuiper. It begins just after Neptune's orbit and extends from 4.5 to approximately 7.5 billion kilometers from the Sun. In this region, the objects have relatively stable orbits aligned with the orbital plane of the planets. The second region, as we've seen, is the scattered disk, a more extensive and chaotic area containing icy objects that were thrown by Neptune into much more elliptical and unstable trajectories. The scattered disk partially overlaps with the Kuiper belt and reaches distances of up to 15 billion kilometers from the Sun. Beyond these two regions, there is an immense spherical cloud composed of icy objects, which begins approximately between 300 and 750 billion kilometers away, about 65 times farther than Neptune, and extends to almost a light-year from the Sun. This region was named the Oort cloud in honor of the astronomer Jan Oort, and it is exactly from here that long-period comets come. So, in summary, the gravity of the giant planets pushed countless icy planetesimals far away from the Sun, while the gravity of the Milky Way itself likely stabilized these orbits in the most distant regions of the solar system, where planetary influence is minimal. These objects then formed the region we now call the Oort cloud. It is believed that the outer part of this cloud contains trillions of objects over 1 km in diameter and billions of bodies about 20 km in diameter. Despite being a populated region, the distance between each object is tens of millions of kilometers. The total mass of the Oort cloud is still a mystery, but using Halley's Comet as a reference, it is estimated to be about 5 times the mass of the Earth. In the past, estimates suggested its mass could be much larger, up to 380 times that of Earth. But recent advances in understanding the sizes of long-period comets have led to more realistic adjustments of these values. Pluto was the first object discovered in the Kuiper belt. 60 years later, in 1992, the object named 1992 QB1 was identified, paving the way for many other discoveries in this region. While we have discovered many objects in the Kuiper belt, we have not yet definitively identified any body that clearly belongs to the Oort cloud. Two interesting candidates are Sedna and the object 2012 VP-113. Both have extremely elliptical and distant orbits, too far to have been directly influenced by Neptune. So the question remains, how did these objects get to where they are today? An intriguing hypothesis is that these bodies originated from the Oort cloud and were perturbed by stars that passed close to our solar system in the past, launching them toward the sun. However, this still remains an unsolved mystery. Another fascinating point is the huge discrepancy in the calculations made by astronomers about how many objects should exist in the Oort cloud since the formation of the solar system. Initially, they estimated about a few tens of billions, but upon observing long-period comets, they realized this number could reach into the trillions. A gigantic difference. One of the hypotheses raised for this discrepancy is that some of these comets have an extrasolar origin, having been captured by the sun during stellar encounters in the early stages of the solar system. Although this idea is still highly speculative. Another even bolder theory suggests the existence of an unknown planet in our solar system, located far beyond Neptune's orbit, the famous Planet 9. This hypothesis arose because many long-period comets have strangely aligned orbits, as if something were influencing their trajectory. Furthermore, certain objects in the Kuiper belt show a similar orbital tendency. This hypothetical planet could have up to 10 times the mass of Earth, but so far its existence has not been confirmed. The region where it would be located is so distant and vast that we could easily miss an entire planet without even noticing its presence. To this day, no space probe has come close to the Oort cloud. Voyager 1, the most distant spacecraft we have ever launched, will take about 300 years just to reach the inner edge of this region and approximately 30,000 years to cross it completely. 4 other space probes, Voyager 2, New Horizons, Pioneer 10, and Pioneer 11, are also currently on trajectories that will take them out of the solar system, but they will already be deactivated by the time they reach the Oort cloud. Still, it might be possible to detect an object from this region if it is launched toward the inner regions of the solar system. In the 80s, a proposal even emerged for the construction of a probe called TIAO, whose objective was to reach a distance of 1,000 astronomical units in 50 years, with one of its main goals being precisely to study the Oort cloud. But unfortunately, this mission never got off the ground. Then, in 2014, a mission called the Whipple mission was proposed to NASA's Discovery program, an observatory specially designed to detect objects in both the Oort cloud and the Kuiper belt. The idea was to place this telescope in orbit around the L2 point and, using a photometer, observe distant stars in search of transits of objects located up to 10,000 astronomical units away. And guess what? Unfortunately, this one also met the same fate as TIAO. The Oort cloud is both a frontier and a mystery, a kind of wall that marks the boundary between the solar system and interstellar space. Despite being so incredibly distant that none of humanity's fastest probes have even managed to get close, the Oort cloud has been telling us its story little by little through the comets that visit us and the strange orbits that defy logic. And it is precisely this distance, this veil of uncertainty, that makes it all so fascinating. This is because the Oort cloud forces us to dream big, to imagine what else might be hidden out there, in the most remote corners of our cosmic backyard. It also reminds us of something fundamental. The solar system doesn't end at Pluto, it doesn't end at the Kuiper belt, it doesn't even end at the limits of the heliosphere. There is an ocean of ice, dust, and possibilities orbiting the sun at distances so immense they border on the surreal. And it is from this vastness that questions arise capable of pushing science forward. Could the sun have captured comets from other systems? Is there really a Planet 9 hidden in the dark? And how many other mysterious bodies are still waiting for their chance to enter the scene, streaking across the skies as unexpected visitors? Por enquanto, Critai a video US English for 10 minutes.